Waterspout. Most people see it and reach for their phone. And honestly, you can't blame them. From a distance, a waterspout looks like something out of a painting. A thin white column connecting a cumulus cloud to the surface of the sea, lit by afternoon sun, surrounded by nothing but open water and blue sky. Sailors have logged them for centuries. Renaissance artists painted them into seascapes. Coastal tourists photograph them constantly off the Florida Keys, zooming in from beach chairs with drinks in hand, uploading the video before it even dissipates. What those tourists are photographing is, in one version, a fully active tornado. Waterspouts split into two completely different phenomena that share only their appearance. The first, tornadic waterspouts, are actual tornadoes that either formed over land from a supercell thunderstorm and moved offshore, or developed directly over water from a rotating storm structure. They carry the same wind field, the same destructive potential, and the same EF scale intensity as any land-based tornado. A tornadic waterspout making landfall doesn't transform into something new. It was always a tornado. It was just temporarily standing on water. The second type is stranger and far more common. Fair weather waterspouts don't form from the top down out of a violent storm. They build from the surface up. Warm, shallow water heats the air directly above it, creating a localized pocket of instability. Under the right conditions of light wind shear, that rising air begins to rotate. A vortex builds upward from the water surface toward the base of a cumulus cloud that may look entirely unthreatening from shore. No anvil, no lightning, no visible rotation anywhere in the cloud. Just a white column standing on the sea like a needle pressed gently into fabric. The Florida Keys see hundreds of fair weather waterspouts per year, more than almost anywhere on Earth, because the warm, shallow waters surrounding them create near-perfect conditions repeatedly throughout the year. The Mediterranean, the Adriatic, the Great Lakes in late summer. They're typically brief, typically weak, and they can come ashore. A fair weather waterspout that makes landfall is reclassified the moment its base touches ground. In 2020, one made landfall near Fort Lauderdale and damaged multiple residential structures before dissipating. No tornado watch had been issued. No severe thunderstorm warning was active. There was no storm to warn about, just a column of rotating water off the coast that drifted the wrong direction. The practical implication is significant. You do not need a supercell, a mesocyclone, or any of the standard warning signs to produce a rotating column of air capable of structural damage. You need warm water, a temperature gradient, and a little wind shear. The ocean provides all three on most days in most seasons across most of the world's coastlines, but water is at least a predictable surface. What comes next forms from something nobody thinks of as a weather system at all: GUSTNADO. Storm chasers know this particular frustration well. You've driven for hours across Kansas following the outflow boundary of a dying thunderstorm. Not the glamorous part of chasing, just methodical repositioning. The main storm has collapsed. The rotation is gone. Warnings are expired. And then, along the leading edge of the outflow, a tight column of dust spins up from the ground and begins picking up debris. From 200 meters, it looks nearly identical to an EF0 tornado. It has the shape, it has the rotation, it has the debris cloud. It is technically, possibly not a tornado. A gustnado forms along the gust front, the surge of cool, dense air that rushes outward from a thunderstorm's downdraft as it hits the surface and spreads horizontally. When that boundary moves fast enough across terrain with sufficient low-level wind shear, brief localized vortices spin up entirely at the surface. They can appear as dust columns, debris swirls, or even loose funnel protrusions from the base of the shelf cloud overhead. They can knock over small structures, overturn vehicles, and injure people standing in the open. The classification debate exists because gustnados often do not connect to the thunderstorm's main rotating updraft and may not link to the cloud base, which is part of the strict definition most meteorologists use for a tornado. The National Weather Service generally will not issue a tornado warning for a gustnado because it's associated with a weakening system. That policy is reasonable. The problem is that it means people can encounter gustnado force winds from a storm system they've been explicitly told is no longer a threat. The warning expired. The radar looked clear. The storm said goodbye. It just didn't go quietly, but at least with a gustnado, there's still a storm nearby to warn you. What comes next offers nothing. No dying storm, no shelf cloud, no gust front. Just a perfectly ordinary October afternoon, and then a funnel dropping out of a cloud that looked like nothing. Cold air funnel, October, Minnesota, or the Upper Peninsula of Michigan, or southern England. The main cold front tore through that morning. Heavy rain, gusty winds, the dramatic part. By afternoon, the sky is clearing. Temperatures have dropped sharply, and the leftover clouds are those small, white, completely ordinary cumulus clouds that you might point out to a child on a nicer day. The atmosphere has moved on. Everyone has moved on. And then one of those clouds drops a funnel toward a field. Cold air funnels form in the unstable shallow layer that trails behind a departing cold front, beneath an upper-level low-pressure system. A developing cumulus cloud creates just enough of a local updraft to stretch weak surface rotation upward into a visible funnel. No supercell, no warm Gulf moisture, no textbook setup. Most extend partway toward the ground, rotate visibly, and retract. But some touch down. When they do, they're typically EF0, minor damage, broken branches, the kind of event that makes local news with shaky cell phone footage. They've been confirmed in Minnesota, Ontario, the United Kingdom, Norway, and several other places where tornado culture essentially doesn't exist, because historically tornadoes were rare enough to be treated as freakish anomalies. Cold air funnels are underreported, understudied, and possibly significantly more common than records show, for the simple reason that they occur in places and seasons where nobody is actively looking for them. Both of these types prove the same thing. The atmosphere doesn't require a severe thunderstorm to produce dangerous rotation. It just needs the right surface conditions, and it finds them in places nobody expects. But those are still weak events. What comes next brings the violence back from a direction nobody saw coming. Fire whirl. August 2018. The Carr Fire was burning across tens of thousands of acres in Northern California. The town of Redding was under evacuation orders. Firefighters were working containment lines to the south and west. And then inside the burn area, something formed that nobody on the ground immediately recognized for what it was. It moved through an already destroyed neighborhood. It crossed a river. It uprooted trees. When the National Weather Service completed the damage survey, they rated it EF3 equivalent. Winds estimated at 136 to 165 miles per hour. It had traveled over a mile. It had debarked trees, scoured the ground, and thrown structural debris hundreds of meters. It was generated entirely by the fire itself, with no thunderstorm, no frontal system, and no warning. Fire whirls are rotating columns of flame and superheated air that develop during large, intense wildfires when specific atmospheric conditions align. The mechanism is well understood. A large fire generates an enormous and concentrated column of rising hot air. When that column encounters horizontal wind shear, winds at different altitudes moving at different speeds or directions, a common condition near active fire fronts, the column begins to rotate. With enough angular momentum and enough thermal energy feeding the updraft from below, the rotation tightens. It organizes. The fire stops simply burning outward and begins spinning upward. Most fire whirls are small and short-lived, a few feet wide, lasting seconds or minutes, forming at the edge of a burn and dissipating before causing additional destruction. Dramatic on footage, not significantly more dangerous than the fire itself. The Carr Fire whirl was not one of those. It was estimated at over 1,000 feet tall. It didn't just burn the trees in its path, it pulled them out of the ground by the roots. It sent burning debris far beyond the active perimeter, igniting new spot fires in areas that crews hadn't flagged as immediately threatened. Structural damage surveys found patterns consistent with a genuine violent tornado. Ground scour, debarked standing timber, building debris relocated hundreds of meters in coherent directions, indicating organized rotation. Scientifically, fire whirls occupy a classification gray zone. The Carr Fire whirl did not connect to a cumulonimbus cloud base, which is part of the strict formal definition of a tornado. But its damage, its wind field, and its atmospheric dynamics were indistinguishable from those of a confirmed EF3. The National Weather Service's decision to apply the EF scale to it was a deliberate acknowledgement that the phenomenon behaved like a tornado, regardless of whether a cloud was involved. Fire whirls have also been documented during volcanic eruptions, where superheated ash columns rising through wind-sheared air create the same rotational dynamics with a different fuel source. Japan's 1923 Great Kanto earthquake triggered a fire whirl in Tokyo that killed an estimated 38,000 people, sheltering in a single open plaza in under 15 minutes. That event remains one of the deadliest single fire incidents in recorded history. The atmosphere will produce rotation wherever it finds the right thermal and shear ingredients. It does not require a thunderstorm. It does not require a warning system. It requires a heat source, wind shear, and nothing in the way. If fire whirls are tornadoes hiding inside disasters, the next level is a tornado that hides inside what looks like a single ordinary funnel. Multiple vortex tornado. Here is the thing about violent tornadoes that most people, including many people who live in tornado-prone areas, have never been told. The funnel you see on camera is not the whole tornado. A multiple vortex tornado looks from a distance or from aerial footage like a single rotating column. One funnel, one center, one track across the ground. But inside that main circulation, two or three or sometimes four smaller, tighter vortices are spinning rapidly around a common center. Each one makes its own separate contact with the ground. Each one produces localized wind speeds that can significantly exceed the parent tornado's rated average. Each one carves its own distinct path through whatever it crosses. These inner structures are called suction vortices. They typically range from a few meters to perhaps 30 or 40 meters wide, narrow enough that they can pass directly through a structure on one side while leaving the other side relatively intact. Their localized wind speeds can exceed the parent circulation's maximum by enough to produce a full EF category difference. A tornado rated EF3 based on average damage assessment can contain suction vortices producing instantaneous EF5 level winds along tracks only meters wide. This is the mechanism behind one of the most persistently confusing features of post-tornado damage surveys. Complete destruction of one structure standing immediately adjacent to a structure with only moderate damage. It is not random. It is geometry. The suction vortices rotate around the common center while that center moves across the ground. The combined motion of their orbital rotation and their forward translation traces what mathematicians call a cycloid path, a looping, scalloped track through the damage area. When survey teams map high-damage corridors precisely and overlay them, the pattern that emerges is almost mechanical in its regularity. The spacing between damage peaks reflects the orbital speed of the vortices and their count. The 1999 Bridge Creek Moore F5 tornado in Oklahoma produced cycloidal damage patterns clear enough that researchers could work backward to determine how many suction vortices were present and roughly how fast they were orbiting, purely from what they left in the ground. That analysis changed something in how meteorologists approach violent tornado wind estimation. A Doppler radar beam, or a ground-based instrument that happens to catch a suction vortex at peak intensity, records a fundamentally different wind speed than one that samples the circulation between vortices, even if both measurements are taken within seconds of each other from nearly the same location. The peak wind speed of a violent tornado is not a single number. It's a variable that depends on where exactly you were standing and how lucky you were. For survivors, this explains something that has never made instinctive sense. Two houses on the same street, one reduced to a slab, one with a missing roof and standing walls. They experienced the same tornado. What they did not experience is the same part of it. Multiple vortex structure tends to develop when a tornado is intensifying or going through a structural reorganization cycle. The outer funnel can appear relatively calm and organized, even shrinking in visible width, while the suction vortices inside are tightening and producing their highest wind speeds. The tornado looks at that moment like it might be weakening. It is not weakening, it is concentrating. But everything covered so far is still a single storm system, producing one event at a time. What the atmosphere is capable of doing at peak intensity is something else entirely: satellite tornado. Storm chasers have a phrase for a specific moment during a large, violent tornado event, a moment that produces a few seconds of genuine quiet in the vehicle before anyone says anything. It's throwing satellites. A satellite tornado is not a suction vortex inside a single circulation. That was the last level. A satellite tornado is an entirely independent tornado, its own condensation funnel, its own mesocyclone connection, its own ground contact, its own damage path. That orbits a larger, dominant tornado produced by the same parent supercell. Two tornadoes, one storm. The smaller one circling the larger one the way a moon orbits a planet, close enough that their circulations interact, far enough that each one maintains its own separate identity. The conditions required for satellite tornadoes to form involve supercell thunderstorms operating at a level of organizational power that is, by itself, relatively rare. The parent storm must be sustaining enough total rotational energy across a wide enough circulation that a secondary mesocyclone can develop on its outer edge independently of the dominant one, and then sustain a tornado from that secondary rotation while the primary tornado is simultaneously active. This typically means the dominant tornado is already large, already violent, and already producing significant destruction. Adding a satellite to that situation doesn't double the hazard. It multiplies it in ways that existing warning and escape frameworks weren't designed for. May 31st, 2013, El Reno, Oklahoma. The tornado that formed that afternoon became the widest ever measured in the United States, 2.6 miles across at its peak, confirmed by mobile Doppler radar. During its maximum intensity phase, satellite vortices were actively detected orbiting the main circulation. Those satellites contributed to the measured total wind field width and produced tornado-force winds at distances from the visible main funnel that experienced storm chasers had assessed as safe margins. Tim Samaras, one of the most respected tornado researchers in history, responsible for some of the most significant in-situ tornado measurements ever recorded, died that day. Two other experienced researchers died with him. They were not reckless. They were operating at what the visible storm indicated was a reasonable distance. The satellite circulation reached them anyway. The damage surveys from El Reno and from earlier multi-tornado events like the May 3rd, 1999 Oklahoma outbreak reveal what satellite tornadoes look like from the ground afterward. Multiple distinct damage paths, each individually consistent with a confirmed tornado, crossing and weaving through the same corridors in patterns that only make sense when you understand they were produced by separate rotating columns orbiting a common parent. The 1999 outbreak survey was one of the most complex in American tornado research history, not because the storms were confusing, but because what they left behind required accounting for multiple independent, simultaneous tornadoes across the same ground. The visible funnel is not the boundary of a tornado's danger. For large, violent tornadoes at peak intensity, the destructive wind field extends well beyond the condensation funnel's visual edge. Satellite vortices can exist and operate at distances where the main funnel barely looks threatening. The gap between what you can see and where it is actually dangerous to stand is not an estimation error. It is a feature of the phenomenon itself. Researchers studying the upper end of tornado behavior have begun asking whether the El Reno event represents a ceiling or a data point on a distribution that extends further than the observational record currently shows. The EF scale ends at EF5, but the EF scale rates damage to structures. It cannot rate wind speeds over open fields, over water, over terrain, where nothing stood to be destroyed. What the actual maximum wind field of a satellite-producing multi-vortex EF5 is capable of generating in open air with no damage indicators in the path to limit the survey remains scientifically an open question. El Reno was 2.6 miles wide. It had satellites. It killed researchers who thought they were at a safe distance. And it was not the largest storm the atmosphere has ever produced. It was just the largest one we managed to measure. The ones we didn't measure left nothing behind to tell us what they were.